Hi, everybody. Weeks ago, we talked a good deal about normal curves and normal distributions, and I introduced them before. I want to say a few more things about them. So to start this out, here's your super challenge question. Where have you seen this god-awful formula before? You've all seen it. Does it look familiar? I bet you never noticed it before. It was at the very top of your syllabus for the course, okay? All these hapless people gathered underneath a normal distribution formula underneath a normal distribution. Okay, so not to scare you or anything, but this is the function for producing that nice smooth normal curve. Mathematically, you calculate the probability for any given score. Any given value is equal to all this gobbledygook, and you would need to know the population mean, and you would need to know the variance. You see sigma squared is in there, and some other characters. Okay, so for any given score, you can determine how probable it is. All right, so that's what's going to be displayed in a normal curve. So I want to talk about some of these functions of these shapes here. Okay, so in no particular order, these are some of the main characteristics of these shapes. Now, I don't have anything labeled in that curve underneath there, and it occurs to me that students sometimes, when they're first exposed to these, it isn't at all clear what this is supposed to be a graph of. We always talk about normal curves, and very seldom do we ever pause to tell students what's actually being displayed in them in clear enough terms here. Okay, so it's a graph without proper labels on it. Okay, so across the abscissa here on the x-axis, we have some variable, and the example that we're going to use all over the place in this class is intelligence. So we like to think that intelligence is normally distributed in the population. Okay, and so you can have low scores on an intelligence test, the IQ test. You can have a very high score on the IQ test. And theoretically, these things go off in infinite directions. Okay, we like to think that there's always a possibility for someone to do better on an IQ test. That there could, there always could be somebody smarter than the smartest person who's ever perhaps been so far. Okay, and on the other end, there's always a possibility that someone could get a little dumber than the dumbest person that's ever been. Okay, so it does go off into infinite directions here. And I know that's a little bit strange to think about, infinity strange to think about. And we call it a test, and we're all used to taking tests where you can get, none of the answers right, or you can get all of the answers right. And tests typically, don't they usually range from 0 to 100%? An IQ test isn't based on what percentage of questions you got right. So there's no such thing as getting a 0 on an IQ test, and there's no such thing as scoring perfectly on it. Okay, so there's no perfect 100% score. There's no 0% score, and it goes off into infinity. It's able to measure infinite intelligence. Okay, and so in the middle is some middle amount of intelligence. All right, now what's totally lacking in the graph in the background here is a y-axis. Okay, the y-axis is displaying how frequent, how often does the particular score on the x-axis occur. Okay, so the higher the curve goes for a given x, the more frequent, the more likely that score is. So intelligence scores right here in the middle are extremely likely, the most likely scores. Okay, substitute something else for intelligence. Height. Okay, most people are average, and some people are freakishly tall, and some people are freakishly short, but most people are clustered somewhere around the middle here. Okay, and so the more frequent something is, the higher the part of the curve is above it. Okay, so that's what's being displayed in the height. We often sometimes just forget to even draw the labels and numbers or anything when we're talking about these things. Okay, so keep that in mind. All right, so a normal curve is bell-shaped for its resemblance to a bell. And when I talk about them from here on, we're going to be talking about very theoretical things. So we're talking about imagining that we have great big populations, like all people, all right? And if you plot the intelligence or the height or the weight or how smelly all people are, these things tend to cluster in this normal curve, as we've talked about before. All right, so it's a theoretical thing. And so since it's theoretical, we can it can be perfect. And in fact, if we use that mathematical expression here, this will create a nice, perfect, flowing one like we're seeing in some of these graphs here, okay? So they're symmetrical. If I were to cut this thing in half, if I draw a line right down the middle where the middlemost people are, the middlemost scores, it will cut this thing into two mirror images of each other, okay? So it's perfectly symmetrical. As I said earlier, the tails taper off, but they never actually touch the abscissa. They never get down to the abscissa because it's capable of measuring off in infinite directions, okay? So there's infinite scores possible, infinitely low, infinitely high scores possible. These are a family of curves. The one that's in the background here and on all these pictures so far are nice, perfect normal curves, all right? Nice normal curves, all right? But they can be even taller and skinnier, and they can be shorter and fatter and plumper, okay? So it's a whole family, as we've discussed in another video. So we got fancy $10 names for those. They could be platykurtic. Remember the term kurtosis refers to how scrunchy a distribution is, or how fat and floppy it is. Okay, so platykurtic are short, fat, plump ones. Mesokurtic is like what you see on the screen here, middlemost kind of kurtosis. And leptokurtic, remember, means to leap, a leaping distribution. Okay, it's tall and skinny. The tails are all scrunched in together. The scores aren't very variable. Now, remember, as the shape changes, so does the standard deviation. We just got done covering the standard deviation. You saw that as a measure of how scrunchy a distribution is. Okay, if you have a small standard deviation, that means that the scores were very much clustered around their middle. If the standard deviation is bigger, the bigger it gets, the shorter and fatter this distribution is going to be. So standard deviation is completely tied up with the shape of a normal distribution, right? Don't forget that. As I said a moment ago, normal distributions, as we're referring to them here, refer not so much to samples and itty-bitty numbers of people, but to great big, perhaps theoretical populations, all right? And as we said before, parameters refer to populations and statistics refer to samples. So therefore we use Greek letters for parameters like mu instead of x bar, and we'll use x bar for samples. And we'll use the Greek sigma to refer to the standard deviation for a population. And when it's a sample, we will refer to it as S. 100% of all the scores fall under a normal curve. So you can also think of it as some kind of weird, I like to think of it as some kind of weird shaped water balloon, okay? It's a water balloon that holds all of the scores, all of the people, all of the data, all right? And like a water balloon, if a water balloon is laying on the table, it might kind of spread out, okay? So if the scores are allowed to spread out like a water balloon might seep outward, okay, that would indicate that there's a lot of spread, a lot of variability in the data, okay? But grab the tails and push them together, push that water balloon together, and what's going to happen? It's going to get narrower, but that water's got to go somewhere. It's going to go up. The balloon is going to get taller and narrower, okay? So 100% of the scores fall in it. So it's also, maybe think of it as like a blanket over your data, all right? Or a tent containing your data, wall to wall, okay? So a lot of metaphors for it, but don't forget that since it's got a shape, 100% falls within it. We're used to carving up shapes like squares and circles and standard shapes like that. This is just a weird turkey that we're going to learn how to carve up. Kind of looks like a turkey if you kind of use your imagination. We're going to learn how to carve this turkey for Thanksgiving. Okay. So since it's symmetrical and since 100% of the scores fall under it, and since it has a certain geometric characteristics, you can start to specify what percentages lie within certain portions. And that's what we want to use this for. We want to use this to talk about what kinds of percentages, what kind of probabilities are associated with being in certain places on here. What is the probability of having an IQ up here, maybe in this upper tail, okay? What's the probability of having an IQ down in the lower portion, all right? We can take any point on this thing and turn it into a percentage. or a percentile. Okay, now don't be scared by the numbers here. Okay, look at the very bottom first, all right? So at the very bottom underneath this normal curve, there's a scale referring to percentile rank. So if you could imagine that we have tracked down and found the very smartest person on planet Earth that ever was, ever will be, and ever could be, that person would have 100% of the population falling at or below his or her value. Okay, that person would be in the 100th percentile. Conversely, if you found the dumbest person that could ever be, that person would be at the 0th percentile. Is that a word, 0th? Yes, it is now. The 0th percentile. Nobody, 0% of the population scored at or below them. So percentiles are not something to be feared. They just tell you what percent is at or below. If you have the very middlemost IQ score possible, you will have the 50th percentile IQ. 50% of the population is at or below you, and conversely 50% is at and above you. Okay, so you can see how there's different percentiles located on this strip underneath here, but not all of them are there. So where we want to go with this is we want to be able to take any score and figure out what percentile it is. So that's kind of our goal here. That's one of the many goals that we have with a normal distribution, is to convert the data to the raw scores into their percentiles. Since we often think or know that a variable happens to be normally distributed in a population, we can therefore use this standard system to do it, okay? And we're going to use what are called standard scores, okay? Now, the shape is standard. It's normal, okay? That's why we call it a normal distribution or a normal curve, because we can apply all kinds of normal things to it. Like I said earlier, IQ, height, weight, how people smell, on and on and on. The list is endless. But all of these items have different values, all right? IQ and smelliness are completely different things. If we're going to measure them, they're very almost certainly going to have different numbers expressing their values. So the numbers, the data can be enormously different, but we know that they're all normally distributed, so they have something in common. So what we're doing here is we're going to standardize the data into a common scale. So the common scale are called standard scores, or sometimes called z-scores, and I'll get to that soon. So a normal curve with a mean, every normal curve has a mean, I'm sorry. And what we're going to do to standardize it, the way that we're going to standardize it is we're going to just set whatever the mean is to 0, right down in the middle. Now, why 0? Think of it this way. We're talking about we're interested in knowing how far from the mean things are, how far from the mean is a score, so that we can figure out what percentile it is underneath it, okay? So how far away from the middle is the middle? It's a weird question, but that's why we're calling that 0. 0 is the point where how far is the middle from the middle? 0. It's 0 away from the middle. So that's why whatever it is. So IQs tend to, the IQ mean in the population, as we'll see, is 100. I'm going to make up a smelliness index, okay? The Metcalfe smelliness index. We're going to go up and smell people and rate how smelly, how good they smell, how poorly they smell, on the Metcalfe smelliness index. And it ranges from, it could be any number I want. Smelliness numbers range from 50 to 1,000. Don't ask me why. Okay? That's the nature of measuring variables. The scales sometimes vary enormously, and people make them up for all kinds of reasons. Okay? So smelliness can be any number. Okay? So it's a completely different number than intelligence. And so I'm going to standardize it by putting it, whatever the mean is for smelliness, 900. Is the mean smelliness number, all right? Well, how far from the middle is 900? 0. There, I standardized. It's now on the same scale as intelligence, okay? I've got the middles of both of those variables in the middle, where they belong. Okay, enough about that. That's hopefully an easy concept. We're going to take the raw data, and whatever the mean is, we're going to call it 0 and put it in the middle. Now we learned how to calculate standard deviation, so you can take whatever the standard deviation is and think of it as a unit, as a single packet, okay? And we can go up and down the scale the number of standard deviations that we want. Okay, now intelligence happens to have a standard deviation of 15 units on the IQ scale. So the mean is 100, which we now called 0. And we could go up 15 IQ points, and that would be 1 standard deviation. We would march up the scale 1 standard unit, 1 standard deviation, 15 IQ points. On the smelliness scale, I would go up 1 standard deviation, whatever that number is. Okay. I could also go down 15 units or 15 points, which would be 1 standard deviation down. Okay, so I could go up 1, up 2, up 3, down 1, down 2, down 3, and frankly, any fraction I wanted. I could go up 1.5 standard units, 2.5 standard deviation. I could go 0.3 standard deviation units, okay? All right, so whatever the standard deviation is, we'll call it 1. So that's whatever the raw data is, we've got a mean equal to 0 now and a standard deviation equal to 1. Now everything's standardized. Forget the raw numbers, forget the IQ scores, forget the smelliness actual scores. Now everything's on a scale of how many standard units is it away from the middle. How many standard deviations away from the middle is whatever value you want to look up. Okay, all right. Now, this normal curve is a shape like a circle, like a square, like a rectangle, like a triangle, but different. It's a little bit different looking. It's not one of those standard shapes that you learn, but it is a standard shape. Okay, so it turns out it has very knowable quantities, just like a circle or a triangle is. You took a geometry class probably one point in your life and you learned how to carve up circles and carve up triangles and carve up squares. Okay, we're going to learn how to carve up this weird looking turkey. So yours is not to ask why, but it turns out that if I go up 1 standard deviation from the middle, it will cut off a very knowable piece. It's an awkward number, but it will cut off exactly 34.1%, approximately 34.1%. This is rounded. Okay, so this chunk of the turkey right here, I get out my carving knife and I cut right down the middle, and I cut right here, and I intend to put that chunk on my plate. I want that towards the middle chunk of turkey. Okay. If I cut right down the middle and up 1 standard deviation, I've cut off 34.1% of the turkey. Don't ask me how we know that, we just do. The mathematicians have determined these values, and ours is not to question why. We go, okay. All right. Likewise, since it's a symmetrical thing, I could go down the other direction to the left on the scale here, and I could go down 1 standard deviation, and it's a mirror image. So that piece too would be 34.1% of the shape. Okay, so there's awkward numbers in here, but they're very knowable. I'm not asking you to remember them. I don't remember them. They're just up there for clarity's sake. Okay? So they are knowable, and there they are. Now what I do want you to remember is this. Let's combine these things in a simpler picture here for a moment, okay? So I have even less labeled here, but we have a standard shape here, so the mean of 0 in the middle, and we can go up 1, 2, 3 standard deviations, or down 1, 2, 3 standard deviations. And a moment ago we saw numbers like 34.1% on each side of this. We'll add them together, and we have about 68% of the data. So about 68% of the data, 68% of the score, 68% of the population, 68% of this turkey is in this knowable range between -1 and +1 standard deviations. That kind of is going to be our new definition of the word most. Most people have an IQ between those two values. Okay? Most is a very imprecise term. It should be at least 50%. I mean, you shouldn't be running around saying, if you've got, 10% of a population, you shouldn't be calling them most people. Okay? but it's a very vague term, so something more than 50%, but 60%, 80%, 90%, 68%, all of these qualify as most. This will be in stats kind of our definition of the word most, okay? Most of the scores are between -1 and +1 standard deviations. Back to the raw IQ scores, what would that be? If 100 is in the middle and I go up 15, one standard deviation was 15 IQ points. So this would be 115 here. 100 minus 15 is 85, right? So if you have an IQ somewhere between 85 and 115, you are in that category of most. 68% of the population, approximately 68% of the population has an IQ between 85 and 115. We can go down to or up to standard deviations. If we add together these pieces that are underneath here, it turns out those sum up to about 95%. So -2 to +2 standard deviation cuts off about 95% of the data. It's a little bit more closer to a neat, nice round number. 68 is a weird, kind of awkward number unless you're in stats. That's become a, for those of us in stats, 68% is a very whole number. We're used to that number, okay? But the general public is not used to 68% being a meaningful number. But 95 sounds like a nice round number. So 95% of the scores, 95% of the population, 95% of the world would have an IQ or a smelliness or a shoe size or a height or a weight that's somewhere between -2 standard deviations of whatever scale we're talking about and +2 standard deviations. Lastly, if we go out to 3, we would cut off, we're getting close to cutting off just about everybody here. I'm not going to call it everyone. 99.7 is not everybody, okay? Because this is infinite, okay? I could go out to 4, 5, 6, 7, 8, 9, 100 these, standard scores, okay? So if we go out to 3, plus and minus 3, we're getting really close to cutting off everybody. 99.7% of the population. 99.7% of that turkey is going to be on your plate if you cut off just those little tiny pieces and leave them on the platter. Okay? All right. So that's some characteristics of the normal curve and are the beginnings of how we begin to standardize all of this. So our goal again, our immediate goal is going to be, well, I'd like to be able to take any score, any raw score, any smelliness score, any IQ score, any shoe size score, any test score, anything that's normally distributed. I'd like to be able to take any value and try to figure out what percentile is that value. Now, some of them are easy. If you have an IQ of 100, it's right in the middle. Like I said earlier, you're in the 50th percentile. Now we could kind of use we can use a little bit of simple math to figure out some other knowable pieces. So what if I went up 1 standard deviation? What if I go up to an IQ of 115? It's not labeled, but right here would be an IQ of 115, 1 standard deviation up. Well, what percentage of the population is that? What percentile is 115? Well, we had 1/2 in the bottom half, so 50% plus that piece, 34.1, is, like it says underneath there, kind of fuzzy, 84%, approximately 84%. Okay, so if you have an IQ of 115, that puts you in about the 84th percentile. 84% of the world has an IQ matching yours or lower. Okay, about 16% are above you. Okay, that's about 16% remaining above you. Okay, if I go down to an IQ of 85, okay, well, that mirror image that was above you when you had 115 is now below you if you're at 85. So approximately 16% of the population has an IQ of 85 or less. You're in approximately the 16th percentile. Okay, that's all fine and dandy for numbers that land right on these posts. But what if you want to look up a score that's somewhere in between? What if I wanted to look up an IQ of, say, 110? What would an IQ of 110? If that's 115, 110's maybe right about there. Okay. What percentile is that? Okay, I can go down and see, oh, that's 70-something percentile. That's not good enough. I want a more precise Batman-like answer. So that's where we're going to go next time. We'll learn how to convert a raw score to a percentile. See you then.